Welcome to NASA headquarters in Washington, D.C. I'm Steve Cole from the Office of Communications. We're here today to tell you about the start of a new era in how NASA studies our home planet from space. This month, we will launch the first of a series of Earth-observing sensors to be mounted on the exterior of the International Space Station. By the end of the decade, NASA will have 6 instruments on this station, helping scientists better understand our home planet. Today, we have key leaders of this new enterprise here to talk with you, along with the lead scientists on the first 2 instruments scheduled to launch this year. Let me introduce our panelists. Here in Washington are Julie Robinson, Chief Scientist for the ISS program from Johnson Space Center, Steve Volz, Associate Director for Flight Programs in the Earth Science Division at NASA headquarters. And at our field centers, we have, at Johnson Space Center, Melanie Miller, Lead Robotics Officer for the next SpaceX launch. From the Jet Propulsion Laboratory in Pasadena, California, we have Ernesto Rodriguez, Project Scientist for the ISS-RapidScat instrument. And from Goddard Space Flight Center in Greenbelt, Maryland, Matthew McGill, Principal Investigator for the Cloud-Aerosol Transport System instrument, or CATS. After today's presentations, we'll be taking questions from the media here in Washington and on the phone lines. If you're listening on the phone lines, media, to ask a question, please press star 1. We'll also be taking questions online. All you need to do is to post a question with the hashtag AskNASA. For more information on how NASA will be studying Earth from the space station, we have a new webpage put together with lots of information, so please visit that at www.nasa.gov/ISS Earth Science, one word. Okay, let's begin our presentations. First, Julie Robinson. Julie?
Well, thanks, Steve. You know, we're really observing a maturing of the space station as an Earth science platform. These instruments that we're going to be talking about today began being built right after the assembly of the NASA components of the International Space Station were completed in 2011. And they're harbingers of the instruments that are going to be coming forward over subsequent years until we have all 25 external sites are completely full. And this first graphic I'll show you, gives you a sense of where all those external sites are on the space station. The space station has a great capability to support power and data and thermal protection. We have sites on the trusses, which have something we call our external logistics carriers on them. There are 4 of those carriers, and they are able to support both our spares as well as Earth and space science instruments. You can see the alpha magnetic spectrometer, which is directly mounted to a service site on the truss. Then on the Columbus facility, we have external payloads being capable of being mounted, and also on the Japanese experiment module exposed facility, which we call the GEM-EF. The space station has really unique orbit capabilities compared to a typical Earth remote sensing satellite. We have what we call a 51.6 degree inclination. And in the video that you'll see, that they'll start right now, you'll see those orbits. It's really a set of orbits across a day. Now, we call it a 51.6 degree inclination because the space station never goes further north than 51.6 degrees north or further south than 51.6 degrees south. So it never goes over the poles. It also means that it goes over different parts of the Earth at different times each day and with a precessing solar cycle. So over a long period of time, you can see different parts of the Earth at any possible time of day. That's very different than our polar orbiting satellites, which basically cross the equator at exactly the same time every day. The space station is also at 400 kilometers, which compares to 800 kilometers for a typical polar orbiting satellite. And that means it's much closer to the Earth. It can observe things with less magnification required to see the same spatial resolution. And the space station itself provides support systems. It provides power, the entire data system, the thermal protection system. And so it makes it possible to, in a cost-effective way, launch a satellite or launch an instrument and put it on the space station, use all of those resources without having to build all of those things into a brand new satellite. And that can let you test a new technology before making an investment in a free flyer. The space station transportation capacity is integrated. So when we launch a vehicle like SpaceX, we launch both internal things from food for the crew, spare clothes for the crew, all of our research supplies for the crew to use inside the cabin, and we can launch external instruments in the Dragon trunk. And so that means the transportation capability is also built into the space station program. There are two major instruments on orbit today on the space station that are observing the Earth, and I want to tell you a little bit about those. HICO, the hyperspectral imager for the coastal ocean, was originally developed by the Office of Naval Research, which is one of our ISS National Laboratory users, and it was as an innovative naval prototype, but it's since been transferred to NASA support because of the science value of the data for a broad variety of users, both those funded by NASA and also ISS National Lab users. It was launched in September of 2009, and over 10,000 images have been collected for scientists to date. In the next graphic, you'll see some color renditions in sort of red, green, and blue color of some of the coastal features that were measured in 2014. But this is almost misleading in a way because these three colors represent only a fraction of the information about the Earth that is in each hyperspectral image. A hyperspectral imager like HICO has about 100 different bands of information, and that compares to 10 different bands in Landsat or just 3 bands in the color image like you're seeing in the picture you see right now. I wanted to give you one example of some recent data that's been collected from HICO and how that data is being used. So in the next graphic, you'll see data analysis for Monterey Bay, California. And on the left-hand image, you see the sea surface temperature measurements. The purple areas represent the coldest sea surface temperatures, and that's a zone of coastal upwelling where deep ocean waters loaded with nutrients is rising up to the surface. On the right-hand image, you see the analysis from HICO, where HICO's been able to distinguish sediments from chlorophyll. Chlorophyll are the pigments in the algae, and they're a sign of those productive waters. So these kinds of analysis in shallow nearshore areas are very difficult to perform with other sensors, and this is a way that HICO can really give us priceless information about unique and important coastal habitats. Another instrument active on the International Space Station today is ISERV, which stands for ISS Severe Environmental Research and Visualization System. ISERV is linked to a joint venture between NASA and USAID, which the Agency for International Development, which is focused on using remote sensing imagery to help respond to environmental change and to natural disasters around the world. This was a technology prototype, and we didn't even put it outside the space station. In the next graphic, you'll see a picture of Commander Chris Hadfield when the ISERV was first installed back in 2012. And what ISERV is basically a high-end digital camera with a telescope mounting attached to it so that it can look in very high spatial resolution back at the Earth. And it's inside the shirt sleeve environment of the space station, looking out the optical quality window. This is a quick way to do a technology demonstration and test and see if something works well before investing even in an external instrument for ISS or for a satellite. I wanted to show you an example of some recent results from the ISERV project as well. In the next graphic, you'll see an ISERV image of Calgary, Canada, after the floods that occurred in June of 2013. This imagery was taken on the space station, downlinked, and rapidly distributed to the officials in Calgary so they could use the mapping of the floodwater extent to help them in managing their real-time response to the disaster. So with those two examples, and in that bigger picture of there are a number of users coming to the space station, and all of these 25 different sites will be full as we get to the end of the decade, the rest of the briefing is going to be focused on the instruments that are coming up right away and the instruments that are planned for the future that are being funded by NASA's Science Mission Directorate or Science Division. And so Steve Volz will be able to tell you a little bit more about that. Steve?
Okay, thank you, Julie. Within NASA's Earth Science Division, we're engaged in conducting a real comprehensive Earth system science, which means observing the Earth from many different perspectives, many different phenomena at the same time to get the best Earth system we can. You see here on the first graphic, we already have an impressive array of 17 different Earth-observing satellites. These are just the ones NASA has built and flown. There are others that we use as well, and giving us that perspective from space. To this will be added in the very near term. In the next slide, you see the evolution of that, which is the ISS as an instrument platform. And these are other satellites that polar satellites, Earth-observing satellites, and that we are flying within NASA. But the ISS is an introduction now as a new and very capable platform. You've already heard Julie talk about the capabilities, the resources that the ISS provides. And what it allows us to do in our science as we address the science questions is to look specifically, to utilize those resources to design the measurements that take advantage of the high power capabilities of the low altitude, close observing capabilities that the ISS provides, and the frequent servicing and revisiting, which allows us to put an instrument up for a relatively short period of time, test it out, and then go to a longer durations free flyer satellite with that measurement if we so decide. The capability of the ISS as a platform allows us to test out an instrument type in a way that is more cost effective, that we can check it out. It can be higher risk but high return as well, in a way that in space that allows us to move forward with our other satellites. The precessing orbit that Julie mentioned, she mentioned the low inclination, or the 51-degree inclination of the ISS, underflies and flies at different solar viewing angles, the same phenomena we're observing with our polar satellites. And that really allows us to look at the same phenomena at different perspectives, different angles, different times of day, which gives us a much more complete picture of the environment that we're trying to measure. So what you'll see, if you queue up the next one you see here, is the ISS, the ISERV and HICO instruments that Julie already mentioned. That's the start of what we'll see in the near future. Coming up this year, we will have both the RapidScat, and in this image you see RapidScat and CATS, which is the Cloud-Aerosol Transport System satellite instrument will be launched in this calendar year, which will be added to the two that are already there. You'll hear a lot more about both RapidScat and CATS from the project scientists who will be presenting in a few moments, so I won't go into more detail on those. Following these two, we'll have in 2016 the launch of a SAGE-3 and LIS. SAGE-3 is the stratospheric aerosol and gas experiment, which measures basically ozone but a lot of other atmospheric aerosols. It was an instrument actually designed for the ISS 10 years ago and now finally getting into place where it belongs. The Lighting Imaging Sensor LIS is a follow-on of a measurement flown on polar satellites, and it will be launching in 2016. It measures the frequency and occurrence of lightning, and it complements again the polar and the geostationary satellites looking at the same phenomenon. Following the delivery of those in 2017 and 18, we have two new ones. Just this summer, the Earth Science Division selected two new satellite instruments designed specifically for the ISS. As Julie mentioned before, the other instruments have been built or designed over the last few years. These are two that are starting from scratch with the ISS as their platform of choice. So they're starting just selected in July, and are going forward with development in the coming years. The EcoStress one, and launching in 2017, stands for the Ecosystem Spaceborne Thermal Radiometer Experiment on the ISS, and you'll see in this next slide an example of what it can do. This is a picture from Landsat, which shows it measures water content and water availability to vegetation systems. And this is a picture from Landsat, which is showing the relative water stress in vegetation. And where you can clearly see in the center of the U.S. here, drought areas where the water is, you can see the plants are dry, the soil moisture is low, whereas in the other where you see the green and the darker green, there is relatively low water stress. This is a derived product from Landsat. EcoStress will add to this, but also add it at different times of day with different spectrum, multiple bands, which can look at it in many more different characteristics. EcoStress is designed with the project principal investigator is from the Jet Propulsion Lab, and the instrument is being built there as well. The other instrument that has just been selected is the Global Ecosystem Dynamics Investigation. This uses what's called a laser-based system for measuring the forest canopy and CO2 or biological content of vegetation systems. It fires a laser, is similar to what you'll hear about on CATS in a little bit, which bounces off the canopy and gets multiple reflections from various spots in the canopy, and allows you to measure not just the forest height, but also the content, the carbon content of the vegetation. An important measurement of the biological content and the ecosystem health of the system. With the two of these added, we will have an excellent platform showing multiple views of ecosystem health and dynamics within the Earth. Now, with that, I'll turn the platform over to Melanie Miller from the ISS Program Office, who will talk about how these instruments will be delivered to orbit.
Thank you, Steve. So I'm going to talk about how we transfer Earth science instruments to the space station. And first, as an example, I'm going to talk about RapidScat and CATS. They're both brought as external cargo on two different Dragon missions. How this works is the Dragon approaches space station, and our astronauts capture Dragon using Canadarm2. We usually just call it the big arm. After the astronauts have completed the capture, they hand it over to the robo-flight controllers. That's what I do. And we fly the rest of the robotics for the mission from the ground, commanding from mission control. While we then are unpacking the external cargo on the Dragon spacecraft, the astronauts are unpacking the internal cargo. We can make the best use of our docked mission time this way. So first for RapidScat, RapidScat is coming up on the Dragon mission that we call SpaceX 4. After we're done with that installation of Dragon on the ISS, I will pick up our little robot. His name is Dexter, and he's also a Canadian. He's going to help us do the transfer of RapidScat to Columbus to a site we call SDX. And this will be the first time we've used the SDX site. RapidScat comes up in two parts, and I have a graphic here showing those two parts. There's a nadir adapter. The nadir adapter helps point the instrument towards the Earth. And then we also have a RapidScat instrument where the majority of the science is conducted. This will be our first time to assemble a instrument on orbit coming up in two pieces using Dexter. And now I have a video of how this works. So you can see Dexter reaching into the Dragon trunk, and we call this the little arm. This is one of Dexter's arms. Is going to grasp the nadir adapter and carefully pull it out. There's some tight clearances in there, so we have to do a rotation to make sure we stay clear of the instrument before pulling it all the way out. And then we have some big arm maneuvers that we're going to perform to get completely clear before we get all set up for the installation on Columbus. And now you can see the little arm is performing a reconfiguration maneuver to get all set up to install the nadir adapter. And the nadir adapter has a common attach mechanism we call a FRAM that we use all over station for all of our external science. So that's the installation of the nadir adapter. So Dexter releases it at its home site on Columbus and goes back and reaches in the trunk and retrieves the instrument. Now the instrument has a 5-hour thermal clock, which is going to be a challenge for us. We usually have a little bit more time to transfer it. These videos are made using the tool that we use to design the trajectories, but we actually go quite a bit slower to make sure that we don't damage anything or cause any loads on either the instrument or the space station. So there you just saw us get the part of the base of the Dexter out of the way so that we can install the instrument. If we don't get the instrument installed in our first attempt, we will put it back in the trunk and reheat it for 20 hours and then try again on another day. So since we have that short clock, we've already developed a bingo time. And there's the instrument installed on the nadir adapter. And so that's it for the RapidScat operations. After that, after it's installed, then the JPL and Marshall will take over with operating it and powering it up. Next I have, the next one I wanted to talk about is CATS. Now, CATS is brought up on SpaceX 5, and here's an image of the SpaceX 5 trunk. And you can see CATS is off to the side there. That is so on future missions we could bring up multiple instruments. CATS is going to be picked up also by Dexter, and here's a graphic of that. And Dexter spins his arm around because he's trying to come in as far away from the sides of the trunk as he can. Those latches you see there were developed for cats but will be reused for other instruments that are meant to go on the GEM-EF. That's the Japanese Experiment Module External Facility. In this case, we're not going to do the installation on the GEM-EF ourselves with Dexter. We're going to hand it off to the Japanese arm that's called the GEM arm. So this is a graphic of us setting up for that. And you can see we've now parked and we're all lined up with the GEM arm. The GEM arm will then do the final installation into Site 3 on the exposed facility, where cats will be nestled in between other instruments that are already up on space station conducting science. And now I'd like to introduce Ernesto Rodriguez from JPL to talk more about RapidScat.
Thank you, Melanie, and thank you for those wonderful videos. They really make me excited to see what's going to happen later on this year. So RapidScat, or ISS-RapidScat as we call it, is a radar instrument that measures the wind direction and magnitude over the oceans. These are essential climate variables that the scientific community has identified because they push the ocean around and they regulate the transfer between gases, between the atmosphere and the oceans. And of course, they're also critical for weather forecasting. Now, winds over the ocean tend to change very quickly, just as winds over land do. One of the challenges that we've had is to maintain a constellation of instruments across many different space agencies that are able to monitor the changes of wind variability in a daily basis. So in the first figure that you see in the lower panel, you'll see the coverage, the daily coverage of the ASCAT mission. That's a European EUMETSAT instrument. That's another scatterometer in a polar orbit. And what you'll see is that although we get global coverage, there are many holes in the coverage. In the upper slide, or the upper graph that you see there, you'll see the coverage of the ISS-RapidScat. So because the orbit is lower, as Julie mentioned, has lower inclination, we get much better equatorial coverage than does the EUMETSAT instrument ASCAT. When we put the two together, as you see in the next graph, in the next figure, so if we could have if we put the two of them together, we actually see that over 90% of the Earth will be covered every day. And so this is really exciting for us. There are many phenomena that change on a daily basis. And as you see in the next figure, this is a view of the Katrina hurricane as it approached New Orleans in 2005. During that time, Katrina was intensifying rather quickly, and it was very important to get daily glimpses at the changes in Katrina, and the same is true for many other hurricanes that tend to change from day to day. By combining the capabilities of these two scatterometers, we'll be able to get global monitoring every day, and we'll be able to provide better forecasting capabilities to operational agencies such as NOAA. If you go to the next animation, please. One of the things that we do beyond getting better numerical weather forecasting or beyond better weather prediction is we provide a global picture, and this is really a unique thing that you can do from space. We provide the first ever global understanding of what the winds over the ocean look like. What you see in this movie is the wind speed as color, going from 0 to 10 meters per second, or if you're a sailor, from about 0 to about 22 knots. And the arrows in the animation are the direction that the wind takes. And what we've done here is average those snapshots that we've gotten over 10 years from the QuickScat mission and made what we call a climatology. That's a view of what the Earth does every month throughout the entire year. Before the advent of spaceborne measurements, we really had no information over a large part of the ocean, and we couldn't understand the processes that were really determining how the energy from the sun goes into the winds and goes into the water of the ocean. The next slide shows one of the unique capabilities of the ISS-RapidScat. As Julie mentioned earlier, ISS-RapidScat can monitor every place on the Earth at a different time of day. Now, why is that important? For the winds, it's very important because winds are driven by the sun. And the sun rises, heats up the atmosphere. Once the atmosphere is hot, winds start to circulate and they start to go up into the atmosphere, carrying water moisture and organizing precipitation and the overall dance between the ocean, the atmosphere, the rainfall, and so forth. This is one of the critical processes in the tropics. So far, as shown in this picture, we've been able to get a very short glimpse of what was going on for a small region of the Earth. What we hope from RapidScat is that we'll be able to get a much better glimpse of what's going on. So what you see in that picture is the daily variability of the winds. And basically, the winds will trace an ellipse of the period of the day. They'll reverse directions, and those processes help to train the winds to move moisture up into the atmosphere, and they also regulate the wind transfer between land and the ocean. So we hope to be able to study the seasonal variability of these wind changes, as well as the variability over a period of 2 years. And with that, I'll pass on the baton to Matt, so he can talk to you about the CATS instrument.
Thank you. The Cloud-Aerosol Transport System, or CATS, is a new instrument for the space station that will measure and characterize the worldwide distribution of clouds and tiny aerosol particles, or tiny atmospheric particles, in the Earth's atmosphere. CATS is a spectacular opportunity to utilize the space station infrastructure to obtain important Earth science measurements at a modest cost. As the first instrument for Earth science to be developed at Goddard Space Flight Center and installed on space station, CATS will provide capabilities that haven't been demonstrated before from space. CATS is a laser remote sensing instrument, or LiDAR, that provides measurements of clouds and particles in the Earth's atmosphere. LiDAR works a lot like radar, except we use low-energy pulses of visible and near-visible laser light. The CATS instrument consists of 2 lasers, each having different characteristics, a receiving telescope, and special photon counting detectors. Overall, CATS packs a significant scientific capability and a lot of technology into a package about the size of a household refrigerator. LiDAR works by sending discrete pulses of laser light into the atmosphere and then detecting the small fraction of light that scatters from particles. CATS will generate profiles of clouds and particles in the Earth's atmosphere to identify the presence and height of clouds and particulate layers. Detailed observations of clouds and particles in the Earth's atmosphere are important for many reasons, but 3 key uses are for providing information on real-time hazard events such as volcanic eruptions, for studies of energy balance, that's climate change, and for examining the effects of man-made and natural pollutants on air quality, health effects. Let's take each of these 3 points in order. For example, CATS can determine the top and bottom height of volcanic plumes. That information can be used to make better decisions on airplane routings and cancellations. The volcanic eruption in Iceland in 2010 resulted in almost 100,000 canceled flights and cost nearly $2 billion because airlines dare not send planes anywhere into or near plumes for fear of damaging the engines. Second, CATS permits studies of clouds. Clouds are one of the largest uncertainties in predicting climate change because clouds are the key regulator of the planet's average temperature. For scientists to create more accurate climate models, they have to include better representations of clouds, which means they need more information on which to base their models. And third, small particles such as dust blown from deserts, smoke from intense forest fires, or man-made pollutants can have significant impact on the Earth's climate and on human health and air quality. CATS data will also be used to improve computer models of clouds and aerosol particles. Right now, the vertical distributions and the microphysical properties of atmospheric particles are often poorly resolved by computer models. To improve the quality of the simulations requires real-time data about the particle type and height. LiDAR can provide that vertical distribution, and we know that will address one of the biggest weaknesses in the models at this moment. The space station orbit is a good fit for CATS because the station transits over and along primary aerosol transport routes in the atmosphere. Data from CATS will be transmitted to the ground continuously and in near real time to be promptly assimilated into computer models to create improvements in those models. That real-time data capability is made possible by the space station communications infrastructure. On the whole, CATS is a cost-effective way to demonstrate new technologies and new measurements that will inform future satellite missions. The build-to-cost approach embraced by the CATS team is a fiscally responsible way to obtain important Earth science measurements, and being able to utilize the space station as a platform begins a new and exciting era for Earth science. And that, in a nutshell, is the why and the wherefore of CATS. CATS is set to launch later this year on SpaceX 5, and we are very much looking forward to this exciting new Earth science capability. And with that, we go back to Steve Cole at NASA headquarters.
Okay, thank you, Matt, and thank you to all our presenters. We'll now take questions from media here in the NASA headquarters, on the phone lines. If you're media on the phone line, again, to ask a question, press *1. On social media, if you'd like to post a question using Twitter, use the hashtag AskNASA. We'll start here with questions in the audience. Dan Leone, Space News.
Hey everybody, Dan Leone with Space News. So when you're doing Earth science and you want to get global coverage and you want to see the same spot in the same condition, there's an orbit for that. If you want to do Earth science and you want to just look down at the same place for as long as your satellite has gas in it, there's an orbit for that. It seems like the ISS, despite the convenient centralization of power, thermal protection, crew time, and communications, is possibly an unhappy medium in a compromise orbit for looking down at the planet. But I've also heard a lot of good reasons today for why people like this. So in a nutshell, why not just build a polar orbiting satellite or geosynchronous satellites? Like, aren't you going to get scientifically better data compared with what you'll get from the space station orbit?
I'll take that one, I think. As I mentioned at the start, we're looking at Earth system science, and Earth system science requires you to do a global view. And global is not just global look at the whole Earth from any one perspective. It's global looking at how it evolves over time. And the diurnal cycle is a pretty critical element of that time. The soil moisture at 6 a.m., if you walk in your grass, is full of dew. At 4 p.m., it may be dry. So if I have a sun-synchronous orbiter looking at it at 4 p.m., I have one measurement of the soil moisture. Then I have at 6 a.m. And both of them are true, but they're not telling you about the entire system. If you have a combination of multiple views at multiple angles or perspectives, the geosynchronous gives you the stare feature, as you mentioned, the geostationary, I mean. The polar orbit gives you a constant variable, constant measurement at a particular time, which allows you to look at long-term variations at that particular time of day. The precessing orbit, the variable angle orbit, allows you to see how that particular phenomenon, any particular phenomenon, varies from different hours of the day. It takes a lot longer to get a massive database at 6 a.m., 7 a.m., 8 a.m., etc., but it gives you a different perspective, which allows you to sort of leverage and see how what you see at one point of view varies from time to time. And this is that soil moisture is just one. Wind speeds vary by the day. The way the vegetation reflects light is highly variable with the light angle. So seeing it from different angles, you get different perspectives on how the vegetation health is as well. So I don't see it as a compromise as much as a complement to the different features that we have from the polar and from the geostationary. You need multiple angles to get a complex system understood, and by having the station adds another variable which we don't have in other ways. We do have some precessing orbit satellites. The TRIM satellite, for example, the GPM, Global Precipitation Measurement, also use variable sun angles, variable times of the day, not sun angles because they're radars, to measure the phenomena. But they're addressing a different piece of science. So the precessing variable crossing orbit time is another tool in the toolbox that we use for measuring Earth system science.
Okay, we have a couple of questions on the phone lines. We'll go to those next. First, Miriam Kramer from space.com. Go ahead, Miriam.
Hi, thanks so much. This question might be for Melanie or whoever would like to answer it. So I'm just curious, is SpaceX 4 still targeted for no earlier than the 19th? And is there any room or any news on the launch date? And also, when is SpaceX 5 expected to go, assuming everything remains on the schedule it is now?
So I'll take that one. SpaceX 4, as you probably know, was no earlier than September 19th, waiting for the successful AsiaSat launch. They're a commercial launch provider, and they've got to work those launches in sequence. That was a successful launch. And so they're expecting to announce their confirmed launch date probably tomorrow, but certainly the 19th is still a possibility, as are several days right after that. So we will hear that from them, I think, tomorrow.
Okay, we have the next question.
Oh yeah,
yes,
for the
that's right.
question
The
on
second
the
about
CATS
the
launch.
SpaceX 5.
The further you get out, the less certainty there is, and so we're still targeting late in the year for SpaceX 5, and we'll pin that down much more closely as we get information from SpaceX and after they get SpaceX 4 under their belt.
Okay, thank you, Julie. Our next question from the phone lines is from Frank Mooring at Aviation Week. Go ahead, Frank.
Thank you. I was interested in what Dr. Robinson said about using the station as a sort of a test platform for Earth observation sensors that could lead to free-flying satellites. I wonder, and I guess I should address this to Steve Bowles, if there are plans in any of the planned Earth observation instruments going to the station to extend them onto a free flyer if they work out on the station. And also, if there are other sensors planned to go on the station besides the ones that have been mentioned today. Thank you.
I'll take the first part. As we talked about the value of the station as a place to test out technologies before maybe a major multi-$100 million investment or in an instrument or a fully free-flying satellite, the space station provides the strong initial step in that. Now, there are no specific plans to take an instrument of any of the ones we mentioned and follow it up with a more capable, more long-duration satellite. On the other hand, the measurement techniques that will be demonstrated by CATS or by JEDI or EcoStress are highly desirable measurements that we hope that will be providing critical information for us. And if you might have noticed, they're very similar to some of the other measurement concepts that have been viewed in our decadal surveys and our other strategic science objectives. For example, and I'll speak specifically to EcoStress, multispectral measurements of the thermal IR imagery of the Earth is a feature of our long-standing Landsat satellites. It's one band on Landsat 7, 2 bands on Landsat 8. Looking at it from multiple bands with a new technology is definitely part of NASA's efforts to invest in new technologies to get enhanced views of phenomena that we've been studying for many years. So successful demonstration by any or all of these instruments would certainly lead to desires to, would influence our decisions on how to go about getting the longer-term measurements. I wouldn't say, though, specifically any one of these is a precursor for a future mission. Julie, you can address the other question.
Sure. So just some examples of some other instruments that are going up. Of course, we've been focused on NASA Earth Science-funded instruments today, but there are instruments in astrophysics, instruments in heliophysics, there are instruments from our international partners, and there are instruments from commercial users of ISS as a national laboratory, all in the suite of things that will go up and fill all these external sites. A couple examples of that, NOAA recently selected TSIS, the Total Solar Irradiance Spectrometer, for ISS. We haven't got that pinned down to location yet, but that's in work in the planning stages. There are 2 commercially partnered external platforms that are designed for rapidly switching out smaller instruments as a test bed concept, and one is called MUSES, developed by Teledyne Brown Engineering, and the other is called NREP, NanoRacks external platform, and those will be able to robotically install small instruments, host them for say 1 to 2 years, and prove out something ahead of a larger instrument development project. They also will be supporting a number of commercial users, particularly in areas of oil and natural resource exploration, and also in areas of high precision crop management. So there are specific instruments and commercial partnerships that will use those platforms as well. So those are just some examples.
Okay, thank you. And I believe we have a few questions on social media. Felicia?
Yes, Steve. So Bob asks, how much more can we learn studying the Earth from the outside in? And the ISS is a modern wonder. Can it continue indefinitely?
That sounds like 2 different questions there.
You take the first. You take the second. I'll take the first.
Okay. So just for the lifespan of ISS, we built it and certified it from an engineering perspective to last for 30 years. And that 30-year time frame comes up in 2028. Now, that doesn't necessarily mean Congress has funded us to operate until 2028. Right now, the entire partnership is committed to operate until at least 2020, and our direction in the congressional language is not to do anything that would keep us from extending. Early this year, the president's office announced that they would like to extend ISS to at least 2024, and that's still in work with Congress. But certainly from an engineering perspective, we could definitely go to 2028 and perhaps longer. So when you see all of these instruments go up, this is a huge opportunity as these instruments become important parts of our data collection system. It's not just a 1 or a 2 year thing. These could extend out for and provide service for a really long period of time.
And I confess I don't quite understand what the first question was.
Observe Earth from space.
Well, it's really only from space that you can get the global perspective. The Earth as a system, we know that the measuring a particular phenomenon, the air quality, the air weather, heat, the temperature, et cetera, is variable from place to place. And by looking at it from a system, and you saw one of the models that Matt McGill showed, looking at the aerosol models, the Earth operates as an integrated system. So you have to observe it that way and in multiple frequencies, multiple phenomena at once to understand how the sea surface temperature affects the moisture in the air, affects the cloud formation, the aerosols affect, the winds affect how these are distributed. So you only see that from space, and you really need that integrated view to get an idea of how all these different variables play together.
Thank you. And the other question we have is from Wim. He asks if CATS is capable of detecting the cirrus clouds that produce sundogs with sufficient precision to predict where they are visible. It's a very specific question.
Yep, that would be a question for you, Matt, at Goddard.
Yeah, any LiDAR instrument like CATS is perfectly suited to observing ice clouds. Ice clouds are the ones that create the sundogs when the sun shines through them. And those are a primary focus of LiDAR measurements because the ice clouds have a big impact on radiative balance of the atmosphere. I think what the person is asking is, can we tell the difference between visible and subvisible cirrus? And the answer is yes, we can with the LiDAR data. And so that is exactly what CATS likes to do, and that's exactly what the LiDARs are good at doing.
Okay, thank you for that, Matt. We have one more question on the phone lines. Frank Mooring again from Aviation Week. Go ahead, Frank.
Thanks, Steve. This one is for Melanie Miller down at JSC. I just wanted to make sure I understood. Is this the first time that y'all have used Dexter and the big arm in conjunction to extract payload and install it somewhere, or has that been done before? And also, if you have any examples looking ahead of other times when you plan to do this.
Melanie at JSC?
Yes, actually this will be the second time we've used Dexter in the trunk. On SpaceX 3, we pulled out HDEV and Opals and installed them on station. So SpaceX 4 will be the second time we do an extraction from the trunk. It will be the first time that we've assembled a payload using Dexter, and also the first time we've built procedures and are prepared to reinstall something into the trunk. And that's only if we exceed the instrument's thermal clock. We'll go ahead and put it back, heat it up, and try another time. So we had to develop that installation. As far as future missions, there's several other SpaceX missions that are manifested that we use Dexter to pull things out. Some of them are for station cargo, like the docking adapters that we're going to bring up in the trunk. Every SpaceX mission has a cargo. Some of the cargo's being pulled out by the big arm, and some of the cargo's being pulled out by Dexter. But it's pretty full manifest.
Okay, thank you, Melanie. We have one more question on social media. Felicia?
So Ryan asks, how much data is stored by CATS and how is it transmitted? And kind of related to that, once the instruments are installed, how long will it take to start collecting data and sending it back to Earth?
So maybe Matt should start with the question about how much data.
Sure. CATS generates on average about 2 megabits per second of data, which is well within the continuous downlink capability of the space station. And we are one of the first ones to do continuous and big data flow from the space station using their comlink. So it's been a forcing function there. And I guess, Julie, do you want to answer the question about how quickly after we're installed?
Yeah, so I don't have the numbers in front of me for CATS in particular, but each instrument has its own startup and checkout phase that that is set by the specifics of the instrument. Once it's installed, then it's connected to all thermal connections and so forth, so it's in a safe configuration. And then they'll take their time to do a series of checkouts and things like that, make sure the instrument's communicating its health and status back before they start up. And then a lot of times people will call that first image down first light when the first data collection comes. And that can be anywhere from a few weeks to a few months after the instrument gets on orbit, depending on how things go. One other thing I should mention about the ISS is, unlike any other satellite where you launch it and it's up there, we can upgrade our data system. So we've already done several data system upgrades over the years, and that allows us to expand our data capability so it can support these different multiple instruments. And so we keep looking and talking with our users about what they're going to need and get ahead of that. Just like at home, you've got to upgrade your router at home every now and then because you get more and more devices. We're doing the same thing on the space station.
And Ernesto at JPL, I think, wanted to respond to that as well.
Yes, we actually will be getting data from the instrument a few days after the mechanical installation. We don't expect that data to be immediately useful. We'll be tuning it to get the better calibration. So that period may take 1 or 2 months. But given the fact that the RapidScat instrument is very similar to the QuickScan instrument, we're very hopeful to get useful data to the science community early on after our turn on.
Okay, thank you, Ernesto. And that's all the questions we have for today, so we'll wrap up the briefing. As you're probably aware, this is a very busy year for NASA Earth Science, including the CATS and RapidScat launches. We have 5 launches scheduled in one 12-month period, which is pretty unusual. We have a website where you can keep up with all this activity, as well as the new research results and airborne campaigns NASA has going this year. That website is www.nasa.gov/EarthRightNow. And of course, you can follow along with all the NASA activities in human exploration and scientific discovery on social media, on all the channels that we have out there to keep you updated on all this activity. Well, thanks everybody for your participation and for watching. Have a great day.